Okay. So, hi Aditya. Uh, is my am I audible, Aditya? Can you let me know in chat or by thumbs up if I'm audible? Okay, sure. So it seems like today no one else is coming to the session, so we'll just start with the session right away. So let me share my screen first. So so just to introduce myself again for the people who will be watching on YouTube and who might be new to this session. So hello everyone, this is session 5 of NPTEL Discrete Maths course, and I'm Lakshya Saggi, problem solving TA for Discrete Maths course for basically this session, and I take the Tuesday sessions for this. So yeah, so in today's session we'll be discussing problems based on like mathematical induction and pigeonhole principle. So let me share my screen and we'll start right away. Yeah. So is my screen visible, Aditya? Okay, cool. It's visible. So let's just start straight away. So today's session I think will be pretty easy, but still, let's go through it. So the first question basically says that suppose there are n people in a town and which have a name of lengths greater than 3. So basically this statement says that there are n people and each of those people has like a name where the length of the name is greater than 3. So basically the name contains more than 3 alphabets. So what is the number of people in the town such that you are guaranteed to find at least 2 people with the same second alphabet in their name? Okay. So this question is based on pigeonhole principle, but let's just see what the question is saying. So basically, it's saying that there are n people with greater than 3 alphabets in name, and we need to find, uh, and what we need is at least 2 people with same second alphabet. So for this straightforward approach, it's a straightforward question. So basically, uh, let's just see. Basically, there are like 20 since there are 26 alphabets in English from A to E, A to Z. So basically, second alphabet has 26 choices. For any name, there are 26 choices for the second alphabet. I suppose my name is Lakshay, so my second alphabet is A. My name second alphabet is A. Your name is Aditya, so your name second alphabet is D. So basically, there are like 26 choices for streets from A to Z. So in the worst case, what can happen is this question is basically related to pigeonhole principle. So in worst case, what can happen is suppose we pick 26 different people. So all of those people have like different alphabets, in their name. So first guy has suppose A as the as the second alphabet in his or her name, and second guy has B, third guy has C. So similarly, 26 people can have this 26 choices, and after that, the 27th person uh, will have uh, basically will have a repeated alphabet. But since this is because like 26 people have different from A to Z, so 27% will have one of the alphabets from A to Z as the second alphabet. So that guy or girl will have repeated one of the alphabets. So for 27 people, we can be sure that am I making sense, Aditya? So 27 people uh, basically. So if we pick 27 people, 27 distinct different people. So what we are sure to get at least two people with same second alphabet. So I think the logic is pretty clear since there are like 26 choices for the second alphabet. So by pigeonhole principle, so maybe I can write pigeonhole principle here. PHP basically refers to pigeonhole principle. So by PHP, we pick 27 different people. There are 26 choices for alphabet. So one of the alphabet will be repeated. So that's why answer is basically 27 here. So 26 is not possible. So generally what we need to show in these types of question is that for 27 people, we have shown that there will be a repetition. But we need to also show that like there is no case as that like for less than 27 people there can be a case where alphabets are not repeated. So am I making sense? So we have shown a bound of 27 that 27 is possible. Similarly, like suppose I would have told you 50. 50 bound would also have been possible. It would not have been the lowest possible bound. So for showing the lowest possible bound, we also have to show that less than 27 people is not possible, basically. So basically, if I pick 27 people, then there can be a case where their alphabets are not repeated. So to show that 27 is the smallest possible number, we need to show that less than 27 can have different hmm, alphabets. Like alphabets refers to basically second alphabet in the end. Okay, so for this, basically it is easy to show. So we can show for 26 people. So for 26 people, uh, there can be a case that each of the person has alphabet that all okay, I'll just rewrite this that all people have different alphabet A to Z. So am I making sense here? Basically, so 26 is 26 is not possible. So basically what we have shown is 26 is not the correct answer, and basically because in 26 we can find basically first person can have like alphabet as A, second can have alphabet as B, similarly 26% can have alphabet as Z. So 26 is not possible. Here we have found a case where all alphabets are different. But for 27, by pigeonhole principle, we have already told that by being 27 people, we are sure to get at least two people with the same second alphabet. So uh, basically, why I wrote this part, basically to show that 27 is the smallest possible number, is because, like, suppose another person could have come and told you a solution that, suppose 50 is the correct answer. And then that person tells you why 50 is the correct answer because, like, if we are given 50 people, then by Pigeonhole principle, one of the person will have, there will be at least two people with the same second alphabet. But we also need sort of the lowest possible bound for the number of people, right? Because otherwise I could have just told you about a very large number, let's say 1,000 or like 10,000, and I would have told this is the answer. But generally we need to answer in these sort of questions the minimum possible number, if I'm making sense, because we need to find a proper bound. So here like 27 is the best possible answer. So like smallest possible answer. So for showing that this is the smallest possible, we need to show that any number smaller than this won't be a solution. So we have just shown that like for 26 people, 26 won't be a solution as A to Z, these alphabets can be taken by other people also. So 26 is not the correct answer. So I'll just underline and write the answer. Hence 27 is the smallest possible such number. I hope I made sense why I did this smallest part. So let's come to the next question then. So this question, okay, let me just check first if I'm okay recording this. Yeah. Okay. So in the second question, basically again it's based on Pigeonhole principle. So here the question is asking, given a set of integers from 51 to 250, what is the least number of integers that can be selected such that any two of the chosen integers are consecutive? So again, this is a straightforward question based on Pigeonhole principle. So Aditya, would you like to attempt this question? Or would you like to answer it in chat, or should I just explain it right away? Okay, maybe I'll just start explaining, and if you get your answer, you can type in chat as we are solving this question. So basically, there are basically numbers from 51 to 250. So we can see that these are like 200 numbers basically. Like so it's 51, 52, 53 up to 250 consists. This set consists of 200 number. So then so what is the least number of integers that can be selected such that any two of the chosen integers are consecutive? So now we need to show what is the least number of integers. Basically, we need to select such number of integers such that any two of the chosen integers are consecutive. So again, thinking as in the previous question here, suppose we do not pick consecutive numbers, then I can pick numbers of the form. Suppose I pick 51, then I will pick 50, then I can pick 53. Since if I pick 52, they will become consecutive. Then I can pick 55, 57, and similarly so on till basically this will be 249, right? So I can pick 100 numbers which are not consecutive, right? Which don't have any consecutive pair. This is better way of saying this. Similarly, another such set of 100 numbers can be uh, 52, 54, 56, 58, and so on till 250. So here also these are 100 such numbers which don't have any consecutive pairs. So at least we know that 100 is not the correct answer. We'll need to pick more than 100. So basically, what I now want to say is that you can show this using pigeonhole principle. So if I pick another number, suppose this is the set of 100 such numbers which are not consecutive, which don't have any consecutive pair, then I pick yeah, Aditya, 101 is the correct answer. So how we came to this answer? So basically, the set of in this set of 100 numbers, I know that I cannot pick in this set of 100 numbers. I have shown that it doesn't have any consecutive pair. But now, if I pick another number in this set, suppose I have picked 100 numbers and then I pick another number, then that number will be basically one of that number will basically either be 52, 54, 56, 58, or like up to 250. It will be an even number. So then like suppose the picked number is 58, then it will be basically forming a pair with like 57, 58, and 59. So I'll get a consecutive pair if I pick another number in this set. Similarly, in this set of 100 numbers, if I pick another number, then it will be an odd number and it will be like 53, 55, 57. Suppose it was 53, then it will form consecutive pair with 52 and 53, similarly 53 and 54. So basically, if I pick another number after 100 numbers, then I am always guaranteed to have uh, at least two of the chosen like at least one consecutive pair. So I'll just type it up. If I pick another number in the above two sets, then guaranteed to have a consecutive pair. In then guaranteed to have a consecutive pair. Hence, by PHP, basically you can show this in Pigeonhole principle also. You can show the like buckets as suppose like 51, 52, 53, 54, 55, 56, 57, 58. Suppose these are the buckets. And now since these will be 100 buckets, so picking 101 numbers, one of these buckets will have to be fulfilled, if I'm making sense. So basically, suppose we make the buckets as, I'll just type it out here, 101. So formally, how do you write it as? Take the buckets as 51 to 52, then another bucket as basically 53 to 54, similarly up to, so this will be up to 249 to 250. So these will be 100 buckets. So basically, if I choose 101 numbers, one of the buckets will have uh, at least two elements. Uh, and hence these two elements will be consecutive, right? I hope I'm making sense. Since the buckets consist of consecutive numbers only, so this will have this bucket will be filled and it will have like these two numbers. So these will be consecutive. So by Pigeonhole principle, picking 101 numbers guarantees a consecutive pair, right? So and so basically what we have shown that picking 101 numbers guarantees a consecutive pair. And we have also shown instances where picking 100 numbers provides us, and we have also shown an example where picking 100 numbers does not give us any consecutive pair, right? So as I told earlier also, basically we need to show an actual result, like basically we have to show this 101 and we also need to show why this is 101 is the smallest possible. By other arguments, why can't I get less than 101? So you can just see using an example basically to prove that there is a case where picking 100 numbers we still don't have any consecutive pair. You just have to show an example of such kind. So here I've shown an example where there are 100 numbers which don't have any consecutive pair. And for 101, I have formally proved using basically Pigeonhole principle by taking 100 buckets that one of the buckets will have two elements, so which will be consecutive. So by these two statements, basically by showing these 100 numbers which don't have any consecutive pair, and then this argument that 101 numbers guarantees a consecutive pair, we get that 101 is the correct answer. I hope I'm making sense. Basically, I'm trying to write a complete argument where the completeness as in providing a result and proving why it is the best possible result. So both of these together constitute a lower bound. So yeah, let's move on to the next question then. So in the next question, basically, yeah, this question is asking which of the following statements is false. So let's just go over every statement one by one. So Pn is equals to nq minus n is divisible by 3 for all n belongs to z. So basically Pn is n minus 1. Basically Pn is nq minus n. Okay. Yeah. I think you're correct. Your answer is correct. But maybe I'll just type it down for maybe the people who will be watching this on YouTube also. So basically, this you must have seen this in lectures, or you can show by mathematical induction. It's not too hard that this is true. Basically, A is true, and very straightforward argument. You can see maybe you can prove this by induction also. Basically, but if you don't want to show it using induction, you can just see that n cube minus n can be written as basically n times n minus 1 times n plus 1. And since these are three consecutive numbers, n minus 1 and n plus 1, so basically one of these numbers will be divisible by 3. Since if we pick three consecutive numbers, or let's say k consecutive numbers, then one of the numbers must be divisible by k. Like you can, this is the standard pigeonhole principle argument. So I don't think it's very hard to see why is this the case. So hence one of these three factors is divisible by 3. So A is true. So B says that n square is greater than 2n plus 1 for all n belongs to z plus. So z plus basically means the set of positive integers. So basically it's from like 1 to infinity, 1, 2, 3, 4, 5. 0 is not positive. 0 is, so basically, so we can just see for ourselves first, like for just checking whether it is true or not. So n square is greater than 2n plus 1. So let's put n is equals to 1. So on this side, we'll get n square as 1, whereas on right hand side, we'll get 2n plus 1, which is basically 2 times 1 plus 1, which is 3. So it does not hold for n equals to 1. So as it does, so this statement is false, as it does not hold for n is equals to 1. So let's just analyze this statement further so that maybe we can get a better understanding. So I just zoomed in a little bit so you can see more clearly. So basically for n equals to 2 also, this statement is incorrect, right? Since 2 square is equals to 4 and right side will be 2 into 2 plus 1, which is like 4 plus 1, 5. So it does not hold for 2 either. Does it hold for 3? So for 3 it gives like 3 square gives 9 and 2n plus 1, like 2 times 3 gives 6 plus 1, 7. So it holds for 3. And so basically it does not hold for n equals to 1 and 2. So I think you guys can try it out yourself. It will be a good exercise for you. It won't be too hard. So try it yourself. I'll just label it. Is so basically prove that this statement is true for n greater than equals to 3. And hint is use principle of mathematical induction. I'll just check induction. Yeah. So it won't be too hard. Basically, you can see suppose n equals to 3 is the base case. You can show n equals to 3 as we assume like 3 square is 9 and 2 into 3 plus 1, 9 is greater than 7. Then for showing n plus 1 whole square is greater than 2 times n plus 1, like uh, it won't be too difficult. So I'll just leave it at that. So I think it's a good exercise because it can help you gain more intuition and like more practice for induction. So I'll encourage you to try it. So yeah. So option C. Yeah, that's right. Option A. So option B was false. And for option C, what we have pi is 1 plus 3 plus 5 plus up to 2i minus 1 is I square. So this you can show by induction also, but we have already studied in high school also, like this statement is true. So can be proven easily using induction. So can be proven induction. I don't think it's too hard. So basically here, suppose for base case, we have basically here also I will be positive integer. Maybe I have not written that. I'll just write it in here. So for all I belongs to. So for I equals to 1, this trivially holds since this is only left side is 1, right side is also 1. And suppose now I want to show I plus 1 from I. I'll just do this overly, guys, because this is something we learn in high school itself. So right side becomes I plus 1 whole square. And this will then expand to I square plus 2I plus 1. Then I square can be written as this part 1 plus 3 up to 2I minus 1. And the remaining 2I plus 1 term will come from basically the left hand side, because since we are showing for I plus 1, the left side will have sum from 1 plus 3 plus 5 up to 2I plus 1. And from that up to the 2I minus 1 part will be assimilated in I square, and the remaining 2I plus 1 part will go to the remaining expansion from I plus 1 whole square. So basically I plus 1 whole square is 2 I square plus 2I plus 1. So I square will assimilate all of these terms, and then 2I plus 1 can be compensated from another term from the left hand side of the sum. I hope it makes sense. And if it doesn't, you can write it on paper and make sense of it yourself, since it's not too difficult of an exercise. So yeah. So now let's come to option D. So option D says n is less than 2 to the power n for all n belongs to Z. So here note that the domain is Z, not just Z positive. So you'll have to show for all integers, right? So I'll just like preface the discussion for this, that this statement is true. And why is this true? You can just see, like, suppose n is negative, like since n is an integer, it can be like 0, negative or positive. So for negative numbers, it's like very trivial, negative integers, because left hand side will be negative. Maybe I'll just write it down. True. For negative numbers, it is trivial as LHS is negative and RHS is positive. Negative because like n is negative, so this side will be negative, but 2 to the power even negative numbers is a positive number. Positive. For n is greater than equal to 0 can be shown to hold using principle of mathematical induction, using induction. So note that one thing I wanted to point out here is that in this option, basically why I prove this for negative n first, because in using induction, while using induction, you need to prove something for a base case. And then from going from that base case, you need to show that it holds for basically, suppose it holds for base case I, then it holds for I plus 1, I plus 2, and so on. So basically, if you show for I, then you show for everything which is on right side of I on the number line. But you don't say anything about the numbers which are on left side of I. So suppose you don't know whether it is true for I minus 1, I minus 2, I minus 3, and so on. So here, basically, that's why I said that for negative n, we can just give this sort of argument that LH is negative and RH is positive. So now you have shown for like left part of the number line by a straightforward argument, and for now the right part of the number line, you can now show using induction. So basically, my argument is that induction only shows something for one half of the number line, not for the other half. So for the other half, maybe you can use induction of another kind or some other arguments. So here we use some other arguments to show this. And now for n is greater than equal to 0, I can show this to hold using induction. Now, it is also not too hard. You guys can see for yourself. So n equals to 0. First of all, base case holds because left side is 0 and 2 to the power 0 is 1. So 0 is less than 1. And for now, and so now suppose I need to show for n plus 1 also. So for showing, while showing for n plus 1, what I can say is that I'll just do this orally also since it is not too hard. So I'll have like 2 to the power n plus 1 on the right side and I'll have n plus 1 on the left side. So the n part can be written as basically n is less than 2 to the power n by induction hypothesis. And I can also say that 1 is less than 2 to the power n. This is because I'm taking n is greater than equals to 0. So basically 2 to the power 0 is 1 and so 2 to the power 1 is 2. And so basically the 2 to the power n only increases as n increases. So I can say that 2 to the power n is greater than 1 for n is greater than equal to 0. And also we have shown that n is, and we have assumed that n is less than 2 to the power n. So n plus 1 will be less than 2 to the power n plus 2 to the power n, which will be 2 times 2 to the power n, which will be 2 to the power n plus 1. So I hope I'm making sense. If I'm not, you can write it out and show it yourself. I'm not going to type that since I just written that it can be shown using induction, but writing it down properly, it is up to you guys because I think it's very easy and it's already done. These sort of problems are already discussed in high school. So yeah, just giving you the basic idea of how it is done, but you can show the proper arguments by yourself. So basically, answer is option B. Yeah. So now let's come to another question. So question 4 asks basically if the following inequality is true. And what the inequality is, it says that 2 to the power n is less than n factorial for all n great for all n belongs to n. Okay, so I think this is something which is related to your assignment this time also. So I'll not tell you like you have written in the your written your answer is chat Aditya, but I'll not say it out loud because it's related to assignments. So, but just I'll just point out so that this inequality is not true. I'll not tell you when is it true. I'll just tell you that in general it is not true. And why is it not true? Uh, the inequality is false as it doesn't hold. So basically, for this inequality to be true, it should hold for all natural numbers, right? Because it is written that 2 to the power n is less than n factorial for all n belongs to n. So, but basically, suppose we put n equals to 1 here, then LHS is 2 to the power 1, which is 2, and RHS is 1 factorial, which is 1. So this says that 2 is less than 1, which is not true. So the inequality is false as it does not hold for n equals to 1. So there will be some numbers where it will hold true, but sorry, I'm not going to tell you guys what the numbers are because it's a part of your assignment this week. So let's just keep it at that this inequalities are not true in general. So let's come to the fifth question then. So one second. So in the fifth question, basically it's saying that a black colored opaque bag contains 15 red gloves and 15 green gloves. Krishna takes out one glove at random each time. How many gloves must he take out to be sure that he has at least two red gloves? So basically we need two red gloves. So how many gloves will we need to take out? So I think it's a question which is very similar to like the first question where we need to find how many people we need to sample so that we get at least two people in the same second alphabet. Here we need two red gloves. So maybe Aditya, you can try to answer it in chat. Yeah, 17 is the correct answer. So yeah, you're correct, Aditya. So answer is 17. And why is this the answer? So you can see that suppose I take out suppose I take out 17 gloves, or how should I put it? Okay, yeah, just write it down. Suppose we take, like, let's say 17 gloves. Then in the worst case, what can happen is, like, this can be converted into a standard pigeonhole principal argument also, but let's just go along with this. So in the worst case, we'll get 15 green gloves and 2 red gloves, because there are maximum of like 15 green gloves only. So I can get and I need red gloves. So in the worst case, there can be 15 green gloves and only 2 red gloves. So I am guaranteed to have basically 2 red gloves. Since I'm picking like 17 gloves, maximum 15 of them can be green. So at least 2 of them will be red. So for 15, so while taking 17 gloves, I'm always guaranteed that maybe I'll just put it down as an argument. So uh, let's not do this in this way. Basically, saying that in the worst case, and statements like these are a little less formal. Basically, these are not correct proofs. Like, you're saying in the worst case we'll get 15 green gloves, but like defining what the worst case is and something like that is something which I don't personally like, because you are not formalizing things enough for the reader. So maybe I'll just type the argument in some other manner. So suppose we take 17 gloves, then we are guaranteed then a maximum 15 green gloves can be picked. 15 green gloves can be picked. Basically, if then we'll pick less than equals to 15 green gloves as number of green gloves is equals to 15. So basically, if I take 17 gloves, we'll pick 50 at least maximum of 15 green gloves. So since the remaining are red gloves, so basically let us denote like number of red gloves as R, or maybe that's right. Since number of red gloves plus number of green gloves picked is 17, and this number of green gloves picked is less than equals to 15. Hence, number of red gloves picked is greater than equals to 2. So why did I write it in this form? Because now I have not used any heuristic arguments like saying in the worst case or something. Now I have just shown it like using pure maths only. So I have just said that I have just established an inequality which says there are less than equal to 15 green gloves, and the sum is basically 17. So, and for one number is less than equal to 15. So by like proper maths, we can say that number of red gloves will be greater than equals to 2. Not exactly 2, basically 2 or more than 2. And I need this only. Uh, Basically, I need at least 2 red gloves. So I hope I'm making sense. Like, why did I write it in this manner? Now I have not used any heuristic argument like saying, suppose in the worst case. Like, what is the worst case exactly? So it can get a bit confusing to the reader if like this is a straightforward problem, but in more complex problems, writing statements like this is not good enough, because it can be a source of confusion. So always try to write it formally. So yeah. So basically this ensures that, so if we pick 17 gloves, we are guaranteed to have at least 2 red gloves. So I hope I'm making sense. Okay. So now, as last time, so basically what we have established till now is that if we pick 17 gloves, we are guaranteed to have at least two red gloves. Now we also need to show why this 17 is the lowest possible bound. Like if I pick 16 gloves, then I have to show a case where I won't be getting two red gloves. So to show that 17 is the lowest possible bound, suppose instead we pick only 16 gloves. Then then like it's a straightforward argument, basically an extension of the the argument which I used earlier. So then 15 of them. So basically then there exists a case, then there exists a scenario where 15 are green and one is red. So this is a feasible scenario because like there are 15 green gloves and 15 red gloves. So there can be a case like 15, all of them are picked are green and only one is red. So basically then there is scenario. So here our like condition of picking two red gloves is not satisfied. So here gloves is not satisfied. So basically in first argument, we have shown that by using 17 gloves, by taking out 17 gloves, I'm guaranteed to have at least two red gloves. And I shown in the second argument that 17 is the lowest possible bound. Like picking less than 17 will not be correct. So 17 is the lowest possible answer. So I hope this makes sense. Now, like as you may have become familiar with my problem. So generally, I try to give a twist to the problem also. So and try to basically give you a different flavor of the same problem. So suppose now instead what the question asked was suppose like, I'll just type it out. Alternate or another question. Another question from this only, like you can think of it as a continuation of this part. So here earlier the question asked how many gloves must we take out to be sure that we have at least two red gloves. So now instead suppose I ask the question that how many gloves must she take out to be sure that uh, how many gloves must she take out to be sure that there are two gloves of the same color. So basically earlier we wanted two red gloves. Now we can have two green gloves also. So in this case, what do you think will be the answer? Aditya or Hetal, you guys can try to answer it in chat. Like it's an extension of the previous question only, but uh, I'll encourage you guys to try to answer it. Okay, so Aditya, you're writing 17. Do you think 17 is the correct answer in this case? So what we need is how many gloves must he take out to be sure that he has at least two gloves of the same color. So in 17, when did we require these 17 gloves? Basically, we said that 15 green and 2 red, right? The worst case which we established heuristically. So while picking 15 green only, I will have. Okay, you misread 15. So what do you think will be the answer instead? So basically what I meant to say is 17 will not be the correct answer now because like you can achieve a number lower than 17 also. Since in that example, we were picking 15 green and then 2 red. But now if I pick 15 green, I would have already picked at least 2 green, right? So I would have picked 13 extra greens unnecessarily, if I'm making sense. So now what do you think? How many gloves must we try to take out? 15. Uh, and why do you think will it be 15, Aditya? Uh, in 15, I will have like picking by picking up 15 gloves, I'll have a lot of gloves. So Hetal is changing the answer drastically from Aditya. Hetal is saying 4. So you both guys are sort of on the correct path. So basically, the question is asking how many gloves must he take out to be sure that he has at least 2 gloves of the same color. So the same color can be green or red, either of these, right? Uh, what I'm going to tell you is the answer to this is 3. You just need to pick out 3 gloves. Yes, Aditya, 3. Hazel, you have written 4. You were close to it. So why is it 3? So you can just see that uh, suppose we take out red and then green. Red and then green. So basically, I have picked 2 gloves. One is red and one is green. Then the third glove will either be red or green. And in both cases, we'll get a pair of same color. Right? Exactly. So Aditya is typing it down in chat also why the answer will be 3. So 3 can be justified. Basically, all will be green or all will be red. In both cases, the scenario is satisfied, or either 2 will be green and 1 red, or vice versa. And in that case, also, our criteria would be satisfied. So basically, here we'll be needing 3 only. So we'll need 3 colors. And like basically establishing why 3 is the lowest possible bound. We have shown that for 3, that 3 is the correct answer. But why is 3 the lowest possible number? Why can't we take lesser gloves? So for 2 gloves, basically we have shown here only, like suppose if we pick out only 2 gloves, one can be red and other can be green. And in this case, our condition is not satisfied. But if we take out another glove, then it becomes satisfied. So 3 is the minimum possible answer. So am I making sense, guys? Hetal, is it clear to you now why won't it be 4 and instead it will be 3? Okay, cool. It's clear. Nice. So now let's try to go to the 6th question. So it's a straightforward question. I think you guys have done this sort of stuff in lecture also. So this is statement by statement. So it's just asking which of the following statements are true. So if we pick 9 cards from a deck of 52 cards, we are guaranteed that there is a suit with at least 3 cards. So this statement is true. I think you have done this sort of problem in lectures also. And why is this true? This is because uh, basically, if I am basically as there are only 4 suits, so picking 9 cards by PHP, there will be there will exist a suit with at least 3 cards. So there are only 4 suits. So and I'm picking out 9 cards. So I'll have basically there will be a suit with at least 3 cards. I hope it is straightforward using Pigeonhole principle. So because 9 by 4 is basically slightly greater than 2, so it will round out to 3. So we'll have at least 3 cards. So statement 1 is true. So now for statement 2. So for statement 2, if you pick 4 numbers from 1 to 8, then some 2 of them will add up to 9. So what do you guys think? Is this statement true or false? Maybe I'll just write it down. So this statement is false basically. And oh, Aditya, you're writing true. Okay. I'll just preface it by saying that this statement is false because we are picking four numbers from 1 to 8. And I can give you an example. Suppose false as we can pick the four numbers as 1, 3, basically 1, 2, 3, 4. So I have to pick four numbers. So basically from 1 to 8. So suppose I pick 1, 2, 3, 4. Then no two of these will sum up to 9. Yeah. So that's why this statement is false and not true. So be careful, guys. Don't do these sort of mistakes. So just go through the problems carefully. So, so in general, what you can say instead is that. So we have seen that this statement is false for like for four numbers, but for five numbers, this statement will become true. Uh, It will be true if we pick five numbers. And how can you like basically how can you show how it will be true for five numbers? Basically, the argument will be using Pigeonhole principle only. Make buckets as 1, 8. So suppose one bucket consists of the numbers 1, 8. The second bucket consists of numbers 2, 7. Basically, the numbers which sum up to 9. So there will be like five such buckets. Basically 3, 6. Okay, there will be four such buckets and 4, 5. So basically, if I pick five numbers out of these eight numbers, so one of this bucket will get at least two numbers, right, guys? So basically, one of the buckets will be filled, and those two numbers will sum up to 9. So while picking five numbers, uh, we'll be able to get two numbers which sum up to 9. So I hope I'm making sense, guys. So here, like basically for 5, we can show using Pigeonhole principle that we'll always get a sum of 9 use from up here. And using 4, why 5 is the lower bound because in 4 we have given an example where this will not hold. So always try to be careful, guys. Like the answer was 5 and not 4. So this statement was actually false. So try to be careful while answering these sort of questions. And the third question is basically every 2 to the power n into 2 to the power n checkerboard with one square removed can be tiled using trinomial. So this is a very standard problem and this has been discussed in the lecture, NPTEL lecture also. So using induction, you can prove that this statement is true. So I'll just type it down that the statement is true as discussed in the lecture. So basically, I'll underline the two statements. Statement 1 is true and statement is true and statement 2 is false. Okay, so I hope it's clear to you guys. So let's move on to seventh question. Okay. So seventh question basically asks us that the seventh question is basically asking us for positive integer n, 10 to the power n minus 2 is greater than 81 and if. So basically it's establishing this inequality and it's asking what are the bounds of n when this inequality is true. So maybe we can basically try to see its values like basically for smaller values of n. So basically for n equals to 1. So I will just start out by testing it for smaller values and we can so that we can establish a lower bound. So for n equals to 1, this will be false, as we can see, because like 10 to the power, this left side will become 10 to the power minus 1 and right side will be 81. So this inequality will not be true. Similarly, like for n equals to 2 also, this will be 1 and right side will be 162. For n equals to 3, left side will be 10 and right side will be greater. Similarly, for n equals to 4 also, like it's just what I'm doing is just straightforward math. I'm just doing it orally. So you can try it out using calculator and stuff also. So for n equals to 1, 2, 3, 4, this will come out to be false. For n equals to 4, left side will become like 100 and right side will be 360 or something. So it will be false. But for n equals to 5, this will hold true. So basically for n equals to 5, this will hold true as like left side will become 1000 and right side will be like something like 405 if I'm calculating correctly. Yeah. So true for n equals to 5. True for n equals to 5. But what about basically the values which are greater than n equals to 5? So for that, we can actually show that this is true using induction. Using it. So basically we have the base case as n equals to 5, which is true. Then we can show that using induction, we can show that inequality above inequality holds for n is greater than 5 also. So how will you go about this? I think again, this is not too hard of a problem, but maybe I think I'll just prove this one because I've been skipping all of the induction proofs. So let's just see how it will go. So Pn says that maybe I'll just write down as Pi. Pi says that 10 to the power I minus 2 is greater than 81i. Right. And now I need to prove that Pi implies Pi plus 1. And note that we have I is greater than equals to 5. Since base case we have taken as 5. Right. To show that what we can do is suppose we take 10 to the power. We just plug it I plus 1 instead of I. So we take 10 to the power I plus 1 minus 2, which is equals to basically 10 to the power I minus 1. So what we can write it as is basically 10 times. So 10 into 10 raised to the power I minus 2. So I hope I'm making sense what we have written. So basically what I'm doing is I'm just typing out the left side of the inequality for I plus 1, what it will be. So instead of I, I'll put in I plus 1. So it will be 10 to the power I plus 1 minus 2, which will come out to 10 to the power I minus 1, which will be 10 times like basically straightforward algebra. It will be 10 to the power I minus 2 times 10. And from induction hypothesis, we know that 10 to the power I minus 2 is greater than 81 times I. We'll just put in this here. So we know that this will be greater than basically this 10 will come out here straightforward here 10 and then multiplied by I'll substitute this 10 to the power I minus 2 with this 81 times I, since I had assumed that this holds true. So I hope I'm making sense here. So what I have done, is basically just substitute, just establish this inequality that 10 to the power I plus 1 minus 2 is greater than 10 times 81i. And what I actually need on the right side was basically 81 times I plus 1, right? What we need on the right side is 81 times I plus 1. So basically 81i plus 81. And how we can show this is that this can be written as 81i plus 9 times 81i. So basically I have split this 10 into 9 plus 1. So this is basically 1 times 81i plus 9 times 81i. And this 9 times 81i can be basically, since I is at least 5, I can say that this 9 times 81i is at least 81. Right, guys? I can take this 81 out, and then 9i will be at least having a value of 1. In fact, it will be having a lot more value because I is greater than equal to 5, but it will at least be having a value of 1. So I can write it as 81i greater than 81i plus 81, which is basically 81 times I plus 1. Okay, I think it should be clear now that what I was doing. So I hope this makes sense. So basically what we have established is, guys, we established a series of equalities and inequalities, and what we get from like comparing the leftmost term and the rightmost term of from this series is that, so we get basically, so we get that this term is greater than, note that we have some equalities, but we also have some strict inequalities. So in the end, this will translate to a strict inequality only, this term. So 10 to the power I plus 1 minus 2 is greater than 81 times I plus 1. So this is what we intended to prove. This is basically the statement pi plus 1 p of I plus 1. I hope I'm making sense, guys. So basically assuming pi, basically assuming this inequality, we have used this inequality in this part to show that pi plus 1 also holds. So basically what we have shown is, hence pi implies p of I plus 1. And we have also shown that p of 5 is true. Also, p of 5 is true. And we have also shown that like for 4 it was false. Basically, we have shown like by putting in the values only. So basically, hence by induction, p of n is true for n greater than equals to 5. I'm just underlining the important parts. So the correct answer then is basically option D. Okay, Hetal, what step do you want me to repeat? I can repeat it. Can you just tell me like what step should I just discuss the whole answer again, or is there a specific step which you want me to repeat? Okay, maybe I'll just go through this inequality again. So basically, let's just see what we are given. We have to show that if pi holds, then pi plus 1 also holds, right? So we can assume that this is true, like pi is true, that 10 to the power I minus 2 is greater than 81 times I. Now instead, after 81, I value substituted. Okay. So maybe I'll just go through the whole again and like, okay. So basically, I'll just, in short, I'll explain the whole answer again. I think that part will also become clear then. So what we need to show is basically pi, like we can assume that this part is true, that 10 to the power I minus 2 is greater than 81i. And now we need to show basically pi plus 1 also hold. So in LHS of pi plus 1, I'll have 10 to the power I plus 1 minus 2. So I start out with the LHS and I'll try to get it greater than the RHS of pi plus 1. So basically, I think I'll write down the pi plus 1 also to make it a bit more clear. 10 to the power. Mm, second, sorry. So this is something which we need to prove. We don't know whether this is true or not, but we can assume that this is true, right? So I just take the LHS of this pi plus 1, and then I expand this, and then I just write as 10 to the power I minus 1, and then I expand it as 10 times 10 to the power I minus 2. Then I substitute 10 to the power I minus 2 is greater than 81i. So I write it as this, basically 10 times 81i. And then what I do is basically, maybe I'll just write another step. Basically, I write this as, basically I write this 10 as 1 plus 9, or 9 plus 1, let's say, times 81 times I. I hope I'm making sense what I did here. Maybe I'll just type it as instead 1 plus 9. So Hital, what I did here is basically just write as 10 times, just write expand this 10 as 9 plus 1 instead. So this will be 1 plus 9 times like 81i itself, like as in here, this 81i remains same. This 10 is written as 9 plus 1. And now by using distributive properties of multiplication, so basically this will become 1 into 81i plus 9 into 81i. That's what I've written. So 1 times 81i will be this 81i itself, and then this, so basically this one and this 81i will multiply to give this 81i, and this 9 and this 81i will multiply to give this 9 times 81 times I. So and then what I do is I take this 81i as itself, because like in right side of pi plus 1 also I'll need this 81i plus 81 term. So I just keep this 81i aside, and then this 9 times 81 times I. Since I need, basically, I'm keeping in mind what I need on the right side also. So I'm just keep doing these steps, keeping in mind I need to get term of form 81i plus 81. So 81i form of term I have already obtained. And to obtain the term of 81, what I do is I just establish that 9 times, like this 9 times 81 times I will be greater than 81. So I can write all of this is greater than like all of this, and this will just be like 81 times I plus 1. So from this I get the inequality. So the main step here is basically writing 10 as instead 1 plus 9. And after this, basically it just becomes distributive property of multiplication over addition, that I can write as 81 into I times 1 plus 9 into 81i. That's what I've done. 81i plus 9 into 81i. Just like writing 10 into 81i as 81i plus 9 into 81i, and then separating these terms. Is it clear now, Hital? Oh, it's clear. Nice. So let's, so then like this is basically we prove pi plus 1. So by induction pn we get true for n is greater than equals to 5. So option D is correct. So let's come to eighth question. Okay, so eighth question says a basket contains 60 walnuts. A basket containing 60 walnuts was kept in the veranda. 10 squirrels randomly came and took away some walnuts. After some time, gardener found the basket empty. Which of the following conclusions is always true for the above given situation? So the question is basically clear. There were 60 walnuts and they were divided amongst 10 squirrels. Basically, since the basket was empty, so all walnuts were taken by the squirrels. So 60 walnuts were taken by 10 squirrels. Then I have to find out which of the statements is correct. So at least one squirrel went back with at most 6 walnuts. So I Are you going to try to answer this question? I think it's a good question. Basically, it's a good practice. It's very similar to like pigeonhole principle itself. So maybe you guys can try it out and let me know in chat what do you think is the answer for this. So the question is very simple. Basically, there are 60 walnuts and they all of them are divided amongst 10 squirrels. So every walnut belongs to one of the squirrels. Okay. So Aditya is saying option D. Option D is at most one squirrel went back with at most 6 walnuts. Okay. And so Aditya is saying option D. Is option D the only correct option, Aditya? Or is any other option also correct according to you? Maybe you guys, what you can think of is um, uh, try to use pigeonhole principle. Think of the squirrels as basically the holes. So there are 10 holes uh, and 60 pigeons. So basically there are 10 holes and there are like 60 walnuts. So walnuts, think of squirrels as holes and walnuts as pigeons. Since walnuts is something which is being divided, similarly pigeons were divided amongst holes. Similarly here, so there are 10 holes and 60 pigeons, right? So now can you try to think what option should be correct using pigeonhole principle? Like now it's just a question which says that like there are 10 holes and 60 pigeons, then what can you say? Like replace just squirrels by holes and pigeons. One thing I just want to make clear to you guys, sometimes you may get confused. What is the pigeon and what is the hole? Like why am I thinking of squirrels as the holes and walnuts as the pigeons and not the other way around? And I think it's a valid question which you guys might think. So how I try to visualize is that basically the thing which can basically a hole can contain multiple pigeons, but a pigeon can only go to one hole, right, guys? So you should always think of this in this context only. The thing which can be matched to exactly one object will become the pigeon. And so basically here, what can I say is that a squirrel can get multiple walnuts, but one walnut will always go to one squirrel. So similarly, a hole can have multiple pigeons, but a pigeon will always go to one hole only. So since walnut always goes to one squirrel, so you can think of walnut as a pigeon. Since pigeon exactly goes to one pigeon always goes to one hole. Similarly here, one walnut always goes to one squirrel. So that's why I'm saying that walnuts can be thought of as pigeons, and like a hole can contain multiple pigeons. So a squirrel can have multiple walnuts. So that's why I'm thinking of squirrels as the holes. So thinking the other way around, you may get in some trouble, like thinking of squirrels as the pigeons and walnuts as the host, you may get in trouble. And why is that the case? Because basically, like what I said, a, a squirrel can get multiple walnuts, but a walnut will always go to one squirrel. So you should always keep this thing in mind. Otherwise, it can be a great source of confusion in like more complex problems. So always go back to the basics and think of it in this term, that which of the following items can be matched with exactly one of them and the other can be matched to multiple of them. So that's why here you can think of it as 10 holes and 60 pigeons. So maybe I'll just tell you guys the correct answers. So one option which Aditya said D was correct, but another option which will be correct is basically the options will be C. Basically, at least one squirrel went back with at least 6 walnuts. So answer is option C, comma D are correct. So and why are these two options correct? So it's just standard application of pigeonhole principle. So there are like 60 pigeons, 10 holes. So there is at least one hole which contains at least 6 pigeons, right? So similarly, so there is at least one squirrel which has at least 6 walnuts. So and similarly, like it also says the pigeonhole principle also says that there is at most one hole which contains at most 6 pigeons. Or okay, okay. I think I have made a bit mistake here. There is at least one squirrel which went back, and similarly, the option D is not correct. Option A would be correct. Option A, comma C are correct. Uh, does it make sense, Aditya? Why am I saying option A and C are correct? Option D is not correct. Basically, at most one squirrel went back with at most 6 walnuts. This statement is not correct. Suppose, like you can just think of it as counterexample that suppose all 60 in one scenario, all 60 walnuts went to only one squirrel, and all the remaining 9 squirrels had 0 walnuts. In that case, there are 5 squirrels which went back with at most 6 walnuts, not one. So basically, how do you see the pigeonhole principle? So basically, here we have 10 holes and 60 pigeons. So by pigeonhole principle, what we can say is that uh, at least one hole contains basically at least 6 pigeons, and similarly, like following the pigeonhole principle only. Similarly, at least one hole contains at most 6 pigeons. So I think these two statements like basically does this number 6 I obtained just by dividing 60 by 10. So these are just the statements of pigeonhole principle only. Like I have not done any fancy thing, just applied the statements of pigeonhole principle directly. Like at least one hole will contain at least 6 pigeons, and at least one hole will contain at most 6 pigeons. Option A is true. Okay. At least one squirrel went back with at most 6 walnuts. So I think this statement is a direct implication of pigeonhole principle only, right, Hital? So you're asking why is this statement true? So in pigeonhole principle, generally what we do is, isn't this there are two statements for pigeonhole principle. Like suppose there are basically P pigeons and H holes, then there exists at least one hole with at least okay, maybe I'll not write down the statement of pigeon principle. You can just find it in the lecture itself. But to get a proper, but as it is at most 6 wallets means other squirrels have taken less than 6 wallets. No. Hital, the option is saying at least one squirrel went back with at most 6 walnuts. Not all squirrels. So why is this statement true? You can, how you can see it is true. Intuitively, how you can see it is true is suppose like no squirrel. Suppose this statement is saying at least one squirrel went back with at most 6 walnuts. So suppose this statement is not true. Then none of the squirrels went back with at most 6 walnuts, right? Then that means every squirrel went back with at least 7 walnuts. Am I making sense? I'll just type it down also. Suppose A is not true, then no squirrel went back with at most 6 walnuts. Okay, yes. So now, so basically what this means is that, so every squirrel went back with at least 7 walnuts. So since there are 10 squirrels, uh, there should be at least 70 walnuts for this to hold. So am I making sense, Ketan? Suppose A was not true, so no squirrel went back with at most 6 walnuts. So every like each of the 10 squirrel went back with at least 7 walnuts. So since one walnut can only go to one squirrel, so there should be at least 70 walnuts for this to hold. But there are only 60 walnuts. Hence, we obtain a contradiction. So A is true. So am I making sense, Ketan? No? It may mean every squirrel went back with less than 6 walnuts. Hidayat, you have to identify the difference between like at least or like this statement is just saying that at least one squirrel went back with at most 6 walnuts. It's like basically what it's trying to say is that we are suppose we are given any distribution of walnuts among squirrels, then this statement will hold. But it doesn't it this statement specifically doesn't specify this that every squirrel will be going with at most 6 walnuts. It's just saying that at least one squirrel should go with at most 6 walnuts. So you are true that this also contains the case where like every squirrel will be going with at most 6 walnuts, but this case won't be arising in our situation, right? So basically, you have to identify the difference. Basically, uh, we this statement is commenting about these statements are commenting about the distribution of the walnuts amongst the squirrels, right? So there are 60 walnuts and 10 squirrels. Now we have distributed these, and now with respect to these distribution, which of the statement always holds? So we have to say that this statement should hold over all the distributions of walnuts amongst the squirrels, not the other way around. That uh, the all possible cases of this, like all possible cases of this, like every squirrel should have at most 6 walnuts and stuff like that. Uh, this need all these cases we don't need to check. We all what we need instead, what the statement is instead asking us is that what the question is basically saying us is that there are the distribution of walnuts among squirrels. What can we comment on that distribution? So as I said, just this comment, is it true that this comment will hold? Like you're thinking, I think a bit in the wrong direction. You're saying that at least one squirrel went back with at most 6 walnuts will also contain the case that every squirrel went back with at most 6 walnuts. But this case is not arising in our uh, walnuts distribution anyways. So uh, am I making a bit of sense here? Because like what I'm just trying to say is that what we have to comment on is just the distribution of walnuts among the squirrels. So don't confuse it with like taking a special subcase of this and then trying to show that subcase also. So what you're saying is that it may mean every squirrel. So Hital, you're saying it may mean, but it is not exactly meaning that, right? So it may mean every squirrel went back with less than six walnuts, but it's not something like a probability class, or probability or something, probabilistic statement or something. It is a definitive statement which says at least one squirrel went back with at most six walnuts. So the case where every squirrel went back with at most six walnuts is a like proper subset of this case, but we are not talking about that subset. We are talking about this bigger set, whether this bigger set will hold true or not. So, like, suppose you're asking some sort of thing that, so suppose I have given you, let me just try to make sense of your arguments, what you're saying. So, let's just say, like, just orally talk. Like, suppose I give you n equals to 6, and then I give you an inequality, and you have to tell whether it is true or false. N is less than 9. I tell you n is less than 9. Is it true or false? So now what, by your argument, what you're saying is that this may, since if I say this is true, that n is less than 9 is true, then it may mean that n is equals to 1 or n is equal to 2 or n is equal to 3, but we are given that n equal to 6. So by your argument, you will say that this statement is false. But I don't think this argument makes sense, right? Is it more clear now, Lisa? Yeah. As it is at most six walnuts taken by at least one squirrel means other squirrels have taken less than six. No, Hital. This statement does not mean. So what this statement just means is that there is at least one squirrel which has at most six walnuts. Other squirrels can have more than six walnuts also. Like try to like basically we are given like 10 squirrels. Out of those 10 squirrels, like let's just number them squirrel 1, squirrel 2 up to squirrel 10. Out of those 10 squirrels, one of the squirrels will be having less than, this statement only means one of the squirrels will have less than equal to six walnuts. It is just saying that one of the squirrels will have less than equal to six walnuts. It's not saying that all squirrels should have less than equal to six walnuts. It's just saying that one of those 10 squirrels should have less than equal to six walnuts, and all the other nine can have more than six walnuts. It doesn't care. It's just saying that like you can replace this at most by suppose less than equal to symbol. So basically at least one squirrel went back with less than equal to six walnuts, and here with greater than equal to six walnuts, greater than equal to six, and less than equal to six walnuts. So now does the argument make sense? At most six walnuts just means that less than equal to six walnuts. And we're talking about at least one squirrel. Like one of the squirrels has less than equal to six walnuts. We are not commenting out the other squirrels. Other squirrels can have more than six or like less than six. We don't care. We just we are just saying we are just care for one specific squirrel should have less than equal to six walnuts. If that is true, then we are done for this option. Uh, should I move? Okay, like you're satisfied with it? Okay. If further doubt arises in this, you can ask this on discussion forum also. But for now, like uh, you can try to think more on this line of argument. So yeah, let's just move on to next question then. So for this question, just to reiterate, like so option A and C are correct. So at least one squirrel went back with at most six walnuts. And similarly, at least one squirrel went back with at least 6 walnuts. So these two squirrels might be different. This might be squirrel 1 and this might be squirrel 10. So squirrel 10 went back with suppose 10 walnuts and squirrel 1 went back with 5 walnuts. And so these two statements are always correct. But these two squirrels, they can be two different squirrels. This squirrel and this squirrel. So now let's go to ninth question. So ninth question is saying which of the state whether the following statement is true or false. So for all n belonging for all natural numbers n, 6 to the power n minus 1 is a multiple of 5. So I think you guys can answer this question. It is true. So yeah, this is not a difficult question. So this statement is true basically. So and this can be proved using induction. So base case is n equals to 1. And so maybe I'll just try prove this also to help you guys. So basically, let's just assume Pn is the statement that 6 to the power n minus 1 is a multiple of 5, right? So now we know that P1, basically base case is P1. P1 is true as 6 to the power 1 minus 1 is equals to 5. And 5 is a multiple of 5. So base case P1 is true. So now for induction, so basically what we have is Pn is saying that 6 to the power n is a multiple of 5. Sorry. And Pn plus 1 would be Pn plus 1 would be 6 to the power n plus 1 is a multiple of 5. So again, for induction, what we need to show is that we need to show that Pn implies Pn plus 1. So we'll assume that 6 to the power n plus 1, n minus 1 is a multiple of 5. And then we'll try to show that 6 to the power n plus 1 minus 1 is also a multiple of 5. Okay, so let's just try to prove it. So we'll start out with this only, basically Pn plus 1 only. And we'll try basically this number 6 to the power n plus 1 minus 1. And we'll try to show it that this is a multiple of 5. So how can we do this? So here also we'll be using similar ideas as to the previous question which we discussed. So let's just type out 6 to the power n plus 1 minus 1 as like 6 times 6 to the power n minus 1. And again, how I'll write this as Hital, like last time I divided 10 as 1 plus 9. Here what I'll try to do is I'll divide this as this 6 as 5 plus 1. Basically, I'll write this as 5 plus 1 times 6 to the, like this is the similar trick which I applied last time also, where I wrote basically this 10 as, this 10 as 1 plus 9 and then apply distributive properties. So similar arguments will follow here. So why I am doing this is basically I have this term of form 6 to the power n plus 1, but for Pn, for trying to apply Pn, I need term of form 6 to the power n. So just trying to reduce this 6 to the power n plus 1 to 6 to the power n forms. So I just wrote it 6 times 6 to the power n, which is 5 plus 1 times 6 to the power n. And oh, I forgot a minus 1 here. So this will be again like applying distributive properties. This will be 5 times 6 to the power n plus 1 times 6 to the power n, which will like so. Let us check out. So this will be 5 times 6 to the power n plus 6 to the power n minus 1. And so now basically uh, this part 6 to the power n minus 1 is by, as Pn was true, 6 to the power n minus 1 is divisible by 5. And this 5 times 6 to the power n plus n is also divisible by 5 since it has a factor of 5. So since these two numbers are divisible by 5, their addition is also divisible by 5. So this is divisible by 5. I hope. So uh, is my argument clear, guys? Divisible by 5, basically I'll write it down also as 5 into 6 to the power n is divisible by 5 and 6 to the power n minus 1 is divisible. So like 5 times 6 to the power n is divisible by 5 like trivially, and 6 to the power n minus 1 is divisible by 5 because of induction hypothesis. Or maybe I'll just write because P of n is 3. So am I making sense, guys? Hital Aditya, uh, is this correct? Okay, cool. So yeah, able to say nice. So trivially just I divide this 6 as 5 plus 1 and just I wrote it as these two terms, and these two terms individually I have shown that are divisible by 5. So their sum is also divisible by 5. So the whole term is divisible by 5. So basically we have shown the base case P1 is true, and we have also shown that Pn implies Pn plus 1. So hence Pn is true for n is greater than or equals to 1. By induction or like principle of mathematical induction, Pn is true for n is greater than or equals to 1. So let's move on to the next question then. So it's a trivial question. So then I think n by 3. So Aditya, you're answering n by 3, like slightly off. I'll just come to this. Answer would be n by 3 minus 1. So the question is asking like Madhu, Anushka and Prasad bought a white chocolate consisting of n blocks. The chocolate is distributed equally among all the three members. So basically each member will get, so this is, there are n blocks. So each member will get n by 3 blocks, right? So Madhu likes to enjoy the chocolate, having it one block at a time. So how many total breaks does Madhu require to finish her share of chocolate? So first of all, we can easily see that since the chocolate has n blocks and it is divided equally among all three. So first of all, we can easily observe that Madhu will get n by 3 blocks of chocolate, right? Now Madhu likes it one block at a time. So, so basically, like you must have eaten chocolate. So chocolates are generally divided into blocks, and so basically, after breaking one block, you can eat that block, and like Madhu, basically there are n by 3. There are n by 3 blocks, so Madhu will basically break it once so that she gets one block, and she'll eat it, and there will be n by 3 minus one blocks remaining, and then she'll break it and eat it. But when there is only one block left, Madhu will not need to break that block, right? So basically, we need to answer how many total breaks does Madhu require. So suppose Madhu has like 3 blocks. Maybe I'll just write down the structure of chocolate. Suppose, like example, Madhu has 3 blocks. So how can it be like, let's just say that is equal to represents the chocolate and one block of chocolate. This continuous segment of is equal to is one block of chocolate. And similarly, this uh, this divider represents like the divider between the blocks. So suppose there are three blocks of chocolate and suppose first Madhu breaks off the divider at this point to eat this like rightmost block. So she like basically if there are three blocks, then she'll first break off at this point to get eat this block, and then these two blocks of chocolate will remain, and Madhu will need to break it once more to eat this block, and then for the last remaining block, Madhu will not need to break anything because basically she can just since the single block remaining, she can just directly eat this block, right? So she'll not be required to break any block here. So if there were three blocks, Madhu required only two breaks, since there were only two breakpoints at which she needed to break the chalk. So similarly, since there are n by three blocks, so what can happen is basically she'll for eating the first n by 3 minus 1 blocks of chocolate, she'll require one break each. But for eating the last block, basically the last remaining block of the chocolate, so she won't require any breaks now, right? Since she can just eat that block directly. Am I making sense, Aditya? Can you let me know in chat? Okay, now you understand. That's nice. So yeah. So here, if she had three blocks, she required two breaks similarly. So for n by three blocks, she'll require n by 3 minus 1 breaks as one break each for first n by 3 minus 1 blocks. So one break each for eating first n by 3 minus 1 blocks. Then last block can be done. Then without break or maybe like without any break. So option D is correct. Okay, so now comes the 11th question. 11th question is a bit trickier than the previous questions and is a lot more insightful also. Like by this question, you can appreciate the pigeonhole principal property. So basically what this question is asking is, so like suppose we are given or uh, maybe I can just rewrite this question. So suppose you are given any natural number n. So any number, any natural number n you are given. So now what you need to prove is that there always exists some distinct natural numbers. Okay, yeah. So basically what we need to prove is that there always exists a pair of distinct natural numbers a and b. So basically there exist two natural numbers a and b such that 2 raised to power 2 raised to power a minus 2 raised to power 2 raised to power b is divisible by n. So this is an interesting question, I would say. So do you guys understand the question? So basically, let's just first see what's the ordering of the like quantifier. So basically, first of all, we are given any natural number n. Suppose n is fixed. We are given the n, so n is fixed. Like let's say n is 1,000 or n is 10,000 or something. So now what we need to show is that for this specific n, there exists like for n equals to 1,000. Suppose there exists a pair of distinct natural numbers a and b. So there exist two natural numbers a and b which are not equal to each other, such that 2 to the power 2 to the power a minus 2 to the power 2 to the power b is divisible by n. So guys, would you uh, like to try it out in chat? Like, first of all, is the question clear? Can you guys let me know in chat? Okay. So maybe at least the question is clear. So maybe I'll just uh, tell you guys the basic blueprint of the solution. So like this may seem like a very tricky question at first or something like this 2 to the power, what do we do with this 2 to the power 2 to the power a term? Do we need some properties of this or something? So actually you don't need any properties for this. This is just something which I made up this function. Basically for any function f, we can write that. Basically suppose it was any function f, basically we can say that there always exists a pair of distinct natural numbers a b such that f of a minus f of b is divisible by n. And how is it true? So let's just deal with like 2 to the power 2 to the power a only for now. So what we can do is, suppose let's just see what the okay, so how do we proceed with this? Let's just take the function f of x as this function, like basically the function 2 to the power. One second, guys. The equation is 2 to the power 2 to the power x. Right. So suppose we take the function f of x, then basically what we need to show is that a comma b such that f of a minus f of b is divisible by n. Right. So for this, what we can see is, suppose I take this set of numbers. Take the set of numbers. Since x ranges over natural numbers, what I do is f of 1. Suppose f of 1 will come out to some natural number like 2 to the power 2 to the power 1. Similarly, f of 2. And none of these numbers will be equal to each other because it's an increasing function. You can see easily. I'm not going to prove that. So let's just take a set of these n numbers. Let's say f of 1, f of 2, f of 3, up to f of n. Or maybe not n, no, just till f of n plus 1. So basically these will be n plus 1 numbers, and it is easy to see that basically these n plus 1 numbers are distinct, right? Okay, maybe I'll just put the whole question in the next page. So I've taken this set of n plus 1 size. Basically, it consists of f of 1, f of 2, f of 3, up to f of n plus 1. So it has n plus 1 numbers, which are distinct. So now let's just see what would be the remainders of these numbers. So these numbers, maybe I can write them as like, so how can I say this? Okay. So another property which I think you guys would need is that suppose, okay, so okay, let's just see any number, uh, any natural number when divided by n, since n is also a natural number, will leave, what will be the remainder? Leave a remainder either 0, 1, 2. Is this statement clear? Like any natural, so suppose there is any natural number, it is when divided by n, it will leave the remainder either 0, 1, 2 up to n minus 1. I think this statement is trivial, you like using the standard remainder theorem which we studied in high school, that there is basically uh, when dividing a natural number by n, so basically the possible remainders are 0, 1, 2 up to n minus 1. N cannot be remainder because remainder is always less than the quotient. So suppose if quotient was n, then basically the remainder will be either 0, 1, 2 up to n minus 1. So what this means is that so there can be basically, so there are n possible remainders. Right, guys. So there are any natural number when divided by n, there are n possible remainders. So now let's just take this set of numbers and look at the remainders of these numbers when divided by n. So look at the set remainders when numbers set S are divided by n. So basically, let's just see what will be there will be some remainder when f of 1 is divided by n. There will be some remainder when f of 2 is divided, when f of 3 is divided, when f of n is divided, and similarly when f of n plus 1 is divided. Right? So it is clear to you guys till now, right? Yeah, Hital. Okay, I'll share the link to the recording. So no issues there. Okay, Aditya, I had not seen your question in the chat. So sir can here A or B equals to n. Yeah, Aditya, A or B can be equals to n. There can be any natural number. So Ajit, you're asking you can you use mathematical induction? Maybe you can try to use mathematical induction to show this, but I would say that it would be more time consuming and it wouldn't be a pretty method basically. What I'm trying to show is using basically pigeonhole principle, and it's a very general method, like for not just for this form of function, like not just for 2 to the power 2 to the power something function, but for general functions also this sort of argument will hold. Whereas for mathematical induction, you'll have to use some arguments for this special form of function. So maybe you can use mathematical induction, but I don't think it would be pretty. So, okay. So let's just try to use this method only. So till now are the arguments clear? So till now what we established is that there can only be like n possible remainders when divided by n, and we have defined a set of n plus 1 numbers. I hope the statements till now are clear. I have not used any fancy arguments. I have just used the terms which are already known to you guys. So now let's move on. So now looking at the remainders. Aditya, there cannot be n plus 1 possible remainder. So remainder can be either 0, 1, 2, 3. So yeah, even if you include 0, Aditya, on dividing by n, n cannot be a remainder, right? Remainder can only be 0, 1, 2, 3 up to n minus 1. N cannot be like on dividing by 5, 5 cannot be a remainder, right? Remainder is only of the form 0, 1, 2, 3 or 4. So I hope it's clear. So yeah. It's clear, nice. So if we look at the remainders when numbers of the set S are divided by n, so what we can get is that, so let's just see when f of 1 is divided by n, what is the remainder when f of 2 is divided up to f of n plus 1 is divided. So what can happen is that, so let's just think of these remainders as possible wholes, like these numbers 0, 1, 2, 3 up to n minus 1 as the wholes. And these remainders of f of 1 divided by s, f of 2 divided by s as basically the pigeons. Maybe I'll just let us name these remainders. So basically, these numbers set of set S when divided by n. Let us name these remainders as basically R1 and similarly R2 and R3 up to R n plus 1. So basically, what I have done is basically the remainder of f of 1 when divided by n, I have labeled it as R1. F of 2 divided by n, remainder I labeled as R2. F of 3 I labeled as R3. Up to f of n plus 1, I have labeled as Rn plus 1. Okay. So now what can happen is that uh, from 0, these values, the value of R1 can be from 0 to n minus 1, R2 can be 0 to n minus 1, R3 can be 0 to n minus 1, and similarly Rn plus 1 can be 0 to n minus 1. So what we can say is that let's think of these numbers like 0, 1, 2, 3 as n minus these possible remainders as the pigeons or the holes. Okay. So think of the possible remainders 0, 1, 2 up to n minus 1 as the wholes, and the remainders R1 up to Rn plus 1 as the pigeons. So basically these are the possible remainders. These are the n possible remainders from 0 to n minus 1, and the actual remainders which we are getting on dividing these n plus 1 numbers are these R1 to Rn plus 1. So these are the pigeons. So these R1, R2, R3 will have values from this set like 0, 1, 2 up to n minus 1. Right. So now basically what we can say is that by pigeonhole principle, since these are n plus 1, since there are n plus 1 pigeons and n holes, so there will exist a remainder R such that it contains at least uh, two uh, two numbers Ri and Rj. I hope it's clear, guys. Yeah, Hital, why we take functions up to fn plus 1? It was because so that basically we get n plus 1 pigeons, right? We could have taken more than n plus 1, but for applying pigeonhole principle, like I needed to take these 0 to n minus 1 possible remainders as the n holes, right? So I need these n holes. So to apply pigeonhole principle, I need at least n plus 1 pigeons, right? So I'm thinking of these R1, R2 up to Rn plus 1 as the n plus 1 pigeons. So basically, I could have taken more than n plus 1 also, like n plus 2, n plus 3. But my work is also done even if I take like till n plus 1 only. But I need at least n plus 1 to apply the pigeonhole principle. So that's why I take n plus 1. So basically, there will exist a remainder R such that it contains. So basically, what I'm trying to say is that there will exist at least two Ri and Rjs whose value will be whose remainder value will be same. Right. So basically, what I'm trying to say is that so there exists two numbers from set S which will have same remainder on division by n. Okay. So basically, this is what so by pigeonhole principle, what I meant to say was this. So basically, I have taken n plus 1 different numbers and I have the remainder set from 0 to n minus 1, n possible values. So there will exist at least two numbers from the set S which will have the same remainder on division by n. That's all I'm saying by pigeonhole principle. Since I have taken n plus 1 numbers and there are only n possible remainders, so there will be at least two. So there will be two numbers which will have the same remainder. As we have n plus 1 numbers, but only n possible remainders. So this is the only argument which I needed to make. So now basically what I have is that suppose these two numbers are like I and j. So suppose I have, so basically suppose I have fi and fj have same remainder on. Since we are running out of time, I'll just do it a bit quick and maybe we can discuss it again in the next session. Have the same remainder on division by n. So basically here by Pigeonhole principle, I established that there exist two numbers which will have the same remainder on division by n, right? So let those two numbers be fi and fj. They are out of this set. So let those two numbers be fi and fj. Okay, I think I have reduced the font size a bit. I'll just increase it. So yeah, have same remain. So fi, suppose fi and fj have. So they will have the same remainder on division by n. So what we can say is that suppose two numbers have same remainder on division by n, then their difference will be divisible by n. So fi minus fj will be divisible by n. Like this fact is a bit, I think this fact is trivial that suppose two numbers, let's say two numbers are like of the form, let's say both leave the remainder 3, then their difference will be divisible by n. So like I think this sort of argument, like if two numbers have the same remainder on some division, then their difference will be exactly divisible. I think this sort of thing you have studied in high school also. So it is easy to see also. Suppose let's just take n equals to 4 and two numbers, let's say, are 9 and 13. So 9 leaves remainder of 1 on division by 4 and 13 leaves remainder of 1 on division by 4. Then 13 minus 9 will be exactly divisible by 4. As 13 minus 9 equals to 4 and 4 is divisible by 4. So this sort of argument always holds. So using this sort of argument, so basically what we have shown is that there will exist I and j, different I and j are distinct. So there will exist distinct I and j such that fi minus fj will be divisible by n. And fi was basically 2 to the power 2 to the power I and fj was 2 to the power 2 to the power b. So basically we have that. So basically we have this statement. I hope it's clear to you guys. Basically, the main arguments here involved were this argument, which used pigeonhole principle, which said that there are n possible remainders and n plus one numbers. So 2 will have the same remainder. And then this argument that if two numbers have the same remainder, then their difference will be exactly divisible. So these were the two main points for this question. And from this, we have there exists distinct integers that is divisible by n. And note that I have not used any property of 2 to the power 2 to the power x function here. I only use the fact like I have taken it as f of x only. So I've just used Pigeonhole principle. So it can be applied to different forms of functions. So same arguments could have been applied even if I had 2 to the power 2 to the power 2 to the power 2 to the power a, or let's say 5 to the power a or 7 to the power a and stuff like that. Okay, it's clear to you guys? Nice. So Hetal is writing that it's clear. So yeah. So maybe if you guys still have some doubts, we can revisit this solution in the next session also. But or you can watch the recording again on YouTube to understand that better. So, but for now, I'm just saying that these are the main two arguments by which we had to prove, and like we are done now. So okay guys, so this marks the end of this session. These are the only problems which I had prepared for discussion. And Hetal, the link I had already posted the YouTube link in the chat, if I remember correctly. So maybe I'll just post it again in the chat after the meeting. So yeah. So, okay, so today's session will be, I think, uploaded. I think like I take at least 2 or 3 days before uploading the session. So I think today's session I'll upload it by, I think, tomorrow or the day after tomorrow. I think fourth video is now available, Hetal. I had uploaded it just yesterday or the day before, so you can watch it. It is available now on that channel which I posted. Okay. And I'll try to post today's video by tomorrow because I think you guys have your assignment due tomorrow. So yeah, I'll try to post it by tomorrow. So this is it for today's session, guys. So yeah, hope you guys enjoyed it and all the best for the submission tomorrow. So we'll meet again, same timing on Tuesday next week. So we'll meet you guys then. Okay, then bye bye for now. I'll just stop this recording and then you can leave the session.